All right, so we're moving into the part of this chapter that I would say probably most students find the most difficult, and that is how to do titration calculations inside of a titration curve. Now, like I said before, there's actually no new calculations in this. We are going to be using mini ice tables. We use them in buffers. We're also going to use a number of different calculations that we've already done in chapters 15 and thus far in chapter 16. So it's not that anything is new. That's not why things are difficult. Why this is difficult is because it's difficult sometimes to know what calculation you're supposed to do when. And so we can break the titration curve into 4 zones, and that should help at least a little bit. If you can kind of wrap your head around which zone is which, you can kind of do the correct calculation for the correct zone. So for the first zone is our initial pH. So we haven't added any titrants. We are just looking at our substance and its initial concentration, its initial pH. Well, you've done this calculation before. This is just your standard weak acid or weak base equilibrium to find pH. The thing to avoid is just making sure that you don't try to outsmart yourself here. If you should be given a Ka value or a pKa or a Kb value if it's a base. And you can use your standard ice table to solve for the hydronium concentration if it's an acid, or the hydroxide concentration if it's a base, and use that to figure out the pH or the pOH. So we're talking in zone 1, the very fundamentals of equilibrium, chapter 14, beginning of chapter 15. This is also the only zone where we don't need the mini ice table. Because in this zone, we haven't added any base yet. So you're still going to have to do an ice table. You're going to have to do an ice table for both of these zones here. So zone 1, again, zone 1, this is your standard Ka or Kb to find pH calculation, straight out of the beginning of chapter 15. So nothing new. It's just recognizing that that's all that it is at that point. The second zone, again, since we're talking about a weak, strong kind of interaction here, the second zone is going to be a buffer zone. So you're going to set up a mini ice table to figure out what the ratio of base to acid is. And then you'll plug that into the Henderson-Hasselblack equation like you would any other buffer. So this is right along the lines of the calculations we were doing yesterday. I have this much acid. I add this much strong base to it. It converts it to conjugate. Here's my end concentration. Here's my end value. I put those into my ratio. I've got myself a buffer. The third zone happens when we hit the equivalence point. So at the equivalence point, what we will see is a complete conversion of the conjugate acid to the conjugate base, or vice versa, but usually we're looking at weak acid, strong base curves. So we're seeing a complete conversion. So your mini ice table is going to have zeros on the reactant side and just conjugate on the product side. And in that circumstance, now we're dealing with basically a salt hydrolysis problem. So here's the end of chapter 15. And so what we have to do are two things. First of all, we have to convert the millimoles out of the mini ice table into a concentration, and we have to take the Ka value and turn it into a Kb value to do the proper ice table defined pH. So of these calculations, number 3 is the hardest because it's basically two calculations. You've got a mini ice table. You have to flip the equilibrium around, flip the constant around, and do a regular ice table. All that rolled into one. The last one is actually probably the easiest after the equivalence point. After the equivalence point, you're going to have leftover hydroxide ion or leftover hydronium ion if we're talking about a strong acid titration. And what happens there? That's easy. The leftover hydronium or the leftover hydroxide, that's what goes into the pH. Because that extra hydroxide is going to create far more hydroxide than the conjugate base would have. That leftover hydronium is going to make far more hydronium than the conjugate acid would have. So you do a mini ice table, you figure out how many millimoles of the hydroxide are left over after the conjugates reacted away. You turn it into a molarity, you plug that right into the pH equation or the pOH equation. So these calculations are involved. They are definitely involved. We are not going to sugarcoat that at all. There's a lot that goes into them. But this is an important thing. The one thing we do know is that these are familiar calculations. They might be calculations that you've struggled with, especially zone 3. More often than not, people struggle with determining exact pH of salt hydrolysis. And that's basically what zone 3 is. But if you can get yourself at least to that point, you have a better chance of at least doing the right kind of calculation and heading in the right direction. So let's close out this week with a couple of examples of this. What is the pH of a solution that is being titrated when 10 milliliters of 0.1 molar sodium hydroxide has been added to 20 milliliters of 0.1 molar acetic acid? Now, it's not given to us in the problem. The Ka for acetic acid is 1.8 times 10 to the negative fifth. Again, that one comes just from, we use acetic acid all the time. So since the titration is in progress, the first thing that we're going to want to do is create one of those mini ice tables. We're dealing with hydroxide ion reacting with acetic acid. And it's going to make acetate ion and water. So using the millimole method, 10 times 0.1 is 1 millimole. 20 times 0.1 is 2 millimoles. Initially, we had no millimoles of acetate, and we'll leave the water alone. This is a one-way reaction, so limiting reactant wins. So at this stage of the titration, after all of this has been added, we've got 1 millimole of acetate, 1 millimole of acetic acid. Yes. Yes, so we can take these directly into that net ionic form because they're strong bases in this case. We have acetate and acetic acid at the same time. Both are present. This should scream to us buffer. And if it's screaming buffer at us, then we know the next calculation that we have to do. Next calculation is the Henderson-Hasselblack equation. pH is equal to pKa plus the log of base over acid. The negative log of 1.8 times 10 to the negative fifth plus the logarithm, in this case, of 1 over 1. 1 divided by 1 is 1, and the log of 1 is 0. So the pH is equal to the pKa here. 1.8 times 10 to the negative fifth. 4.74. So the real key to this is we do our mini ice table and we assess, we evaluate. Where are we? becomes a matter of recognition. If I have both conjugates present, I know I'm in a buffer. If the reactant side is empty, I know that I'm at the equivalence point. I got to flip everything around and do the salt hydrolysis. If I ran out of conjugate acid and I have leftover hydroxide, I know that I just need to turn that hydroxide into something. Questions about this example? Okay, so the last example that we're going to do today is a lot more involved. This is a representation of the kind of question that you will probably see in a quiz or exam situation when it comes to this kind of concept. We've got 50 milliliters of a 0.350 molar propionic acid solution. Ka is 1.4 times 10 to the negative fifth, and we are titrating it with 0.175 molar sodium hydroxide. Determine the pH at 4 different scenarios. I'm going to give you a little inside tip here. If you're given a problem like this and it's got 4 different calculations to do, you want to guess why there are 4 different calculations to do? You're going to see 1 from each zone. Generally speaking, you're going to see 1 from each zone. So you just kind of log that. Still, you got to do all the calculations and the proofs, because sometimes it gets thrown at you a little bit different. But generally, that's usually what's going to happen. Is you're going to get the initial pH, you're going to get some sort of a buffer, you're going to get the salt hydrolysis, and you're going to get somewhere after the fact. So let's start at the beginning here. Before the titration, the initial concentration, the initial everything for the propionic acid, well, this would just be your straight up Ka to pH ice table. So propionic acid, we're just going to call H prop. Ka for propanoic acid is 1.4 times 10 to the negative fifth. We're just going to set up our standard ice table here. No tricks, no shortcuts. We don't have anything to make a shortcut with. Our initial concentration of propanoic acid, 0.350. Our initial concentrations of the other stuff, zeros. We're going to lose some amount of propanoic acid, gain some amount of each of our products. So at equilibrium, 0.350 minus X, X for the hydronium, X for the propanoate. Now we just keep going. 0.350, given the Ka value, is this a good 5% rule candidate? Yeah. 5% of that is 0.0175. We're a good couple orders of magnitude away there. So we can ignore that negative X term. So 1.4 times 10 to the negative fifth is equal to X squared over 0.350 minus X. If we ignore the X term, it's just X squared over 0.350. 1.4 times 10 to the negative fifth multiplied by 0.35 1.4 times 10 to the negative fifth times 0.35 is, yeah. Sometimes you punch in a number into your calculator and it comes out and you go, there's no way that's right. 4.9 times 10 to the negative sixth is x squared. So x is 2.2 times 10 to the negative third. And so since x is the hydronium concentration, that's what I can do with it next. pH is equal to the negative log of 2.2 times 10 to the negative third, which would be 2.65. Okay, so that's the first one. Again, straightforward. We've seen this before, just not in this application. Because we haven't talked about acids as, you know, precursor to these kinds of calculations, these kinds of titrations. All right, let's take a look at the second one here. So in the second one, we have 30 milliliters of sodium hydroxide being added now. Now, just to keep things in mind, we had 50 milliliters of 0.350 molar propanoic acid, and its Ka is still 1.4 times 10 to the negative fifth. And the NaOH is 0.175 molar. So now that the titration has begun, now we have to look at things from a mini ice table perspective to see where we go from there. So the reaction is hydroxide reacting with the propanoic acid to make water and the propanoate ion. Here we're going to use the millimole method. Save us some time. If we have to go back to concentration, it's not a terribly large leap to take the millimoles back to molarity if we have to. 30 times 0.175 gives us 5.25 millimoles. Of hydroxide. 50 times 0.35 gives us 17.5. And we're starting with zeros over here. Limiting reactants rule. So minus 5.25 minus 5.25 plus 5.25 for the propanoate. At the end of this part of the titration, we have no hydroxide. We have 12.25 millimoles of the propanoic acid, and we have 5.25 millimoles of propanoate. So what we have to recognize here is that I've got some amount of both of the conjugates present. So by definition, that's a buffer. As a buffer, we're going to use the Henderson-Hasselblack equation. pH is equal to pKa plus the log of the base over the acid. pKa is the negative log of 1.4 times 10 to the negative fifth. For B, it's 5.25. For A, it's 12.25. pKa is 4.85. In the logarithm, we're going to have 3 sig figs. So we need 3 decimal places out of this fraction. 5.25 divided by 12.25. Log of that, negative 0.368. So our pH to 2 decimal places is 4.48. All right. Any questions with this one? Again, not nearly as straightforward, but it is a recognition play. This is exactly like what we were doing yesterday, just without the context of a titration. Yesterday, we were just talking about, hey, I've got this buffer system. What happens if I throw this into it? This is exactly the same. Only the context is not me fooling around in the lab, but rather me doing a titration. Any questions? All right, let's look at the third scenario. So we're going to back up here again. This time it's 100 milliliters added. So we have 100 milliliters of 0.175 molar NaOH present. As well as $50 milliliters of 0.350 molar propanoic acid, whose Ka is 1.4 times 10 to the negative fifth. So once again, we need to start from a mini ice table perspective. Again, anywhere other than the beginning, your first calculation needs to be a mini ice table to figure out where we are. So once again, we're talking about hydroxide reacting with the propanoic acid to become water and the propanoate ion. 100 times 0.175 would be 17.5 millimoles. 50 times 0.35 is also 17.5 millimoles. In this case, we have stoichiometric amounts of each. So both of the reactants are going to lose 17.5. And the conjugate base will gain 17.5. So that leaves 0 hydroxide, 0 propanoic acid, and 17.5 millimoles of propanoate. So recognition at this point should indicate, look, I've got nothing left from the reactants. Nothing. All that I have left is the product. So this is the equivalence point. And so we need to treat this like a salt. We've got a saltwater solution now. Because basically all that's left over after this is done is sodium, water, and the propanoate ion. So that's exactly what you would find if you dissolved sodium propanoate in water. So that's why we can treat this like a salt reaction. So 2 things we need to do before we can even set up anything else. First, we need to turn that millimoles into a concentration. The way that we do that is by dividing it by the total volume. Millimoles divided by milliliters will give you molarity, because the millis will basically cancel each other out. If the millis cancel out, it's moles over liters. We know that as molarity. The volume is the 50 plus the 100. So I've got 150 milliliters. So 17.5 millimoles divided by 150 milliliters to 3 significant figures is 0.117 molar. So in our brains, we can interpret this problem now as what is the pH of a 0.117 molar solution of sodium propanoate. The other thing that we need to do is we need to turn this Ka into a Kb, because we know that that propanoate doesn't have a hydrogen to give. It's going to take one. So the second part of this is we need to set up a standard ice table where we basically flip this around. And so what I had said before about we need to flip the equilibrium around, look at this equilibrium expression compared to the one in the mini ice table. We have flipped it around. The only difference is that we're starting with a new concentration of the propanoate and zeros on that product side. Now we need to turn this Ka into a Kb. To do that, remember, we take 1 times 10 to the negative 14th divided by 1.4 times 10 to the negative 5th, the Ka. Which would give us 7.1 times 10 to the negative 10th. Now, it'll often be the case in these kinds of scenarios where that Kb value is not going to be very big. And so unless we're dealing with an extremely small concentration or an unusually stronger version of a weak base, 5% approximation will almost always apply in this scenario, which is going to make things easier for us. Because what it's going to allow us to do is 7.1 times 10 to the negative 10th is approximately equal to x squared over 0.117. .3 times 10 to the negative 11th is equal to x squared, square root of that, 9.1 times 10 to the negative 6th molar is equal to x. That x value is our hydroxide concentration in this case. So we can take this and turn it into POH. POH is equal to the negative log of 9.1 times 10 to the negative 6th which would be 5.04, which means that our pH at 14 minus 5.04 would be equal to 8.96. So of the 4 zones, this one's the most involved because you've got to do the mini ice table. You got to recognize that you are at that spot. You got to flip it around, write a new equilibrium expression, write a new equilibrium constant, solve a second ice table, and then interpret the results of that second ice table. There's a lot that goes into that. But recognition is half of the battle. And if you can recognize where you are, you've got a better chance of at least getting something out of it if we're looking at things just from a partial credit standpoint. All right, questions about this third zone? All right, the fourth zone, we're now looking at 130 milliliters. So let's put that in. 130 milliliters of the 0.175 molar sodium hydroxide we still have the same 17.5 millimoles of propanoic acid. Ka is still 1.4 times 10 to the negative fifth. Now, having done the previous problem, we know that any sodium hydroxide that is added after that is going to just give us hydroxide ions in the solution. So we know that we're in zone 4 if we've done a calculation for zone 3 and the volume is more than that. But we still want to set up our mini ice table because that's going to help to drive and dictate to us what the concentration actually is so that we can figure out the pOH. So once again, we're going to set the same mini ice table. One last time. $130 multiplied by 0.175 is 22.75. Since propanoic acid is now the limiting reactant, we're going to take 17.5 away from each of them. And 17.5 goes to the propanoate. So 22.75 minus 17.5 is 5.25. Now, what we need to recognize here, so let's say that we hadn't done any other examples to this point. We just put it in, this is what we got. How do we recognize that we are in zone 4? We recognize that we're in zone 4 because in all of the other zones, there was 0 hydroxide left over. This is the only one that has ended with some amount of hydroxide at the end. That's how we know we're in zone 4. That's how we know we are after the equivalence point. And so the fact that we have 17.5 millimoles of propanoate ion doesn't matter. Any basicity that we get off of that, we already saw in the previous example. It's not much. pH is less than 9. That 5.25 millimoles is going to generate far more hydroxide. Again, let's just look at the example. This gave us 9.1 times 10 to the negative 6 moles per liter. This is 0.005 moles. Big gap. Big gap between what the propanoate gave us at the equivalence point and what we're getting here afterwards. So we're going to do kind of the same thing, though. We need to turn this into a molarity. So we're going to divide this by the total volume. Remember, this was 50 milliliters. So 50 plus 130 is 180 milliliters. So the concentration of hydroxide is 5.25 divided by 180, which is 0.0292 molar. So again, perspective here. The propanoate gave us something to the negative 6th for the concentration of hydroxide. This is something to the negative 2nd for hydroxide. It's a drop in the bucket comparatively. So we can just ignore that propanoate's contribution. With that value, we can determine the POH. To 3 decimal places, because there are 3 sig figs, 1.3, oh, excuse me, 1.535, which would give us a pH of 12.465. So as I said at the top of this particular lesson, this problem is right at the easiest of the 4. It's either this one or the buffer one. They're both kind of the same. The only difference is you got to know where to get the pH from. Henderson-Hasselblack equation or direct application of the hydronium concentration or the hydroxide in this case. But those are the 4 zones. And so what you're going to work on, and this assignment isn't due for you until actually Monday night. I'm giving you the weekend to kind of look at stuff and make some questions, ask some things. We'll start off Monday with that. And then you've got all of Monday to digest it. We'll look at it Tuesday. Or at least that the assignment will be due Monday night. This will also go hand in hand. You are doing a titration curves lab on Monday afternoon. And so you're going to see some of this stuff in action. You're not going to have to do these kinds of calculations. The calculations you're going to be doing are a little bit different. They will be the subject of your second formal report. But you should find that the second formal report is a lot easier to write than the first one has been. That's generally been the trend. Part of it's a familiarity thing. Part of it is this is just conceptually, this is a little bit easier to get your arms around as opposed to all that kinetic stuff. Any questions before we call it a week? Okay, so you know what to do next. Get your participation point for today and